two windows and a doorway. A window on one wall and then the window on the opposing wall with a doorway on the third wall that's in between the two. So let's put that on paper. So he wants to have a 10-foot by 15-foot room. Now he wants to have 8-foot walls. So you would mark this 8 feet, this 10 feet, and this 15 feet. This is his third wall here. 8 feet tall. This is also 10 feet. He wants to have a window on this wall, and a window on this wall, and a doorway on this wall. The framing is staggered 16 inches apart. So this will be 16 inches right here. So then it goes straight up and down. So it's going to be parallel with the outer wall. He's going to have these going along the wall for support. Now he wants to have his doorway in here, so he's going to have it go up this way, and then it's going to have, he wants it to be a hexagonal header, so there needs to be a diagonal like this, and then it'll go over here, and then a diagonal back down. This forms a right triangle in the framing right here. Now these triangles are going to be isosceles triangles because these two here are going to be congruent. This one is going to be the longer one. So the staggers are all parallel, but this one right here is going to be perpendicular to these parallel ones. Now with the window over here, he wants the same thing, so it's going to be the same thing as this, but it just won't have the triangles in there. So it's going to go down. They're going to be parallel with the outside walls, and there's going to be a window right in this area. He wants it just to be square. Just a regular square window. Now the braces go down, and then, oh, right there. That's a perpendicular line, or perpendicular board going across, causing a 90-degree angle right here. So Billy is going to realize is that there is a lot of geometry in his drawings. The square is the most common geometric shape, and he wanted his room to have some character, so he's going to have his hexagonal shape over here, and then he's going to have a diamond shaped window over here. So this is how the framing works. These are all parallel, causing perpendicular lines, and if you put a diagonal in there, it'll cause a triangle to be built. Now over here, the staggering goes just like this, but he wants to have a diamond window in here. Now this window can't be put in there unless there's framing around it to keep it from moving. It just can't be sitting there. So you build a frame around it, so you got to put a board here and a board here. Now you need to put a perpendicular board to go across here to support this the top of the window, and then you need another perpendicular board to go here to support the bottom window. Now this creates 4 right triangles in the framing. Now these are all congruent. Now these are going to be all congruent as well. So this makes a isosceles triangle because these two are congruent and it's a right triangle. So it's an isosceles right triangle. Now you need to just keep, this is common architecture right here. You just need to put these braces in so if the building moves, it'll keep the window square. And then the framing continues this way, causing more parallel lines. So what Billy is going to realize is there's a lot of parallel lines, a lot of right angles right here, right angles, right angle here. So Billy uses parallel lines, he uses right angles, he uses triangles, He uses geometric shapes for his windows. I mean, this is hexagonal, it's common, is a square, and he's got even a diamond in there. So yeah, that's how it is. Billy also wants to put an in-ground pool in. He puts an in-ground pool in that is 10 by 12 with 6 foot deep on one side, 3 feet deep on the other. And he wants to put a walk around his pool like this for tiles, so you can walk around on tiles and not on dirt. So he's going to use transformation tessellation to do that. He's going to have his pool line side here, creating a square just like so. His pool is going to be 10 by 12. So this is 10 feet here. I'll put it on the inside because I'm going to draw on the outside. 10 feet here, 12 feet here. He wants to lay brick on the outside to walk, so you can jump in and on the side and stuff, and you won't have dirt on your feet. So the bricks are going to be out about this far. I don't know exactly how far he wanted it. He didn't tell me. He's going to lay his bricks using transformation tessellation, like I said, and they're going to be like this. Now, this is one brick here, and then the next one is going to be laid here, and then the next one's going to be laid here, and the next one's going to be laid here, so on and so forth, all the way around the pool like this. So the next thing that Billy wants to sketch down on paper is the inner part of his pool, because he wants to buy himself a liner. So his pool is 10 feet wide, 12 feet long, by 6 feet deep. So we'll take a quick sketch of that. 10 feet, 3 feet. He's going to have a 3-foot section in his pool. A total of 6 feet deep. And then it is 12 feet long. This is going to be 10 feet back here. Now back here, it's going to be 6 feet deep, and about halfway down the pool, it's going to slant down to the 6 feet from the 3 feet deep part. And now there's 3 sections in this pool, so 12 divided by 3 equals 4. So each section is going to be 4 feet long. So we'll sketch that. Now the diagonal part isn't 4 feet. We don't know what that is yet. But the horizontal section is going to be 4 feet, and the vertical part is going to be 3 feet, because 3 here plus 3 here equals 6 here. So this is going to be 3 feet, making a triangle, imaginary triangle, and then up here you can make a triangle here. Now we need to find the surface area of the inner part of the pool, because that's what he's buying a liner for. So here, this is going to be, well, to find area of sections is base times height. So base times height. So 3 times 10 equals 3 feet, so, or 30 feet. So 3 times 10 equals 30. So this section here is 30 feet squared. Okay, now this back section here, we can actually draw a little thing to make it look a little more 3D. And draw this here, and say this here, because that's where it drops off. We'll go straight up with this. Now this section here is going to be 6 by 10, so 10 times 6 equals 60 feet squared. Now, we don't need the top section because he's not going to put a liner over the top. Now we need to find the bottom part. So we'll split it up. We'll find this section, then we'll find the triangular section, and then we'll find this actual base section. So here, the base is 4 feet by 10 feet. So this piece here is going to be 10 times 4 equals 40 feet squared. Now this back section is 4 feet by 10 feet, because this is 10 feet long, so it's going to be 4 times 10 equals 40 feet squared. Now, in order to find this side length, we need to use the Pythagorean theorem. The Pythagorean theorem is a squared plus b squared equals c squared. So 3 is going to be the a, 4 is going to be the b, and c is going to be what we're going to find here. So a equals 3, b equals 4, c equals, we don't know yet. We'll fill that in when we're done. So we're going to draw a little triangle here. We're finding c here, so c equals, we don't know. This base one's 4, this one's 3, so we're going to use the Pythagorean theorem. It's going to be 3 squared plus 4 squared equals c squared. So 3 squared is 9 plus 4 squared, which is 16, equals 25. The square root of 25, because this is going to be 25, is going to be c squared. So the square root of 25 equals 5. So this c part equals 5 feet, making this 5 feet. So 5 feet times 10 feet equals, so we will go 5 times 10 equals 50 feet squared. Now, did we get them all? We got this one, we got the back one, we got this one and that one and that one. So now we need to do the sides. So this section is going to be, we'll make a little section here because it's going to go out. This will be another, so this is 4 feet here, and this will be 4 feet here, and then up here this way is going to be 3 feet, and then down this way is going to be 3 feet, equaling a total of 6 feet. So this bigger square is going to be 3 times 8. So 3 times 8 equals 24 feet squared. Now, because there's two sides of this pool, we'll just multiply this by 2. So we'll go 24 times 2 equals 48. So now that's this side and this side, so we don't have to worry about that anymore. And now we're going to figure out this rectangle and this rectangle, and we're going to do the same thing again. We're going to find this and we're going to multiply it by 2 because there's two sides. So 4 times 6 equals 24. So 4 times 6 equals 24. 24 times 2, because there's two sides, equals 48 feet squared. Now, we need to find this section of the pool on either side. So, because this is 3 by 4, we're going to go use the area formula, but the area formula of a square is base times height, but the area formula of a triangle is base times height divided by 2. So it's going to be base times height divided by 2. So the base is 4 times the height is 3 equals 12 divided by 2 equals 6. Now we're going to multiply that by 2, so theoretically we didn't even have to do this, but just to be sure, we're going to go 6 times 2 equals 12, because there's this side and this side. So now we want to add all the surface areas together to get the total surface area of the entire pool for Billy to buy his liner. So we got 60 plus 48 plus 12 plus 40 plus 50 plus another 40 down here, and a 30 over here, and a 48 up here. Add all that together, giving Billy a total surface area of 328 feet squared. So his pool liner will need to be 328 feet squared. So Billy